The innovative technology we will be discussing today is ultra high performance concrete. My name is Travis Brooks.
I'm Daniel Lantrip.
My name is Laura Schultman.
Here's a quick overview of the topics that we will be discussing in our project. Ultra high performance concrete is a concrete mix design composed of fiber reinforcement and many other additives such as silica fume and water reducers. This allows for higher compressive strengths and longer fire ratings. The table below shows the composition of ultra high performance concrete. Portland cement 28.5% by weight, silica fume 9.3%, ground quartz 8.5%, fine sand 41%, steel fibers 6.3%, super plasticizer 1.2%, and water 5.2%. Motivation for using ultra high performance concrete is to provide more sustainable infrastructure, with as many as 150,000 bridges in the United States being classified as structurally deficient. Ultra high performance concrete could increase the service life of new bridges to well over 100 years. As you see in the figure below, ultra high performance concrete requires less reinforcement steel than standard concrete, which reduces the amount of internal corrosion. Increased construction productivity is provided by the self-leveling and self-consolidating features of UHPC. Rationale of innovative technology. Ultra-performance concrete provides high compressive strengths exceeding 25,000 psi, or 5 times that of standard concrete, as well as extremely high ductility and durability.
Next, we have a description of innovative techniques and methods as related to ultra-high performance concrete. This includes the use of steel and organic fiber additives for strength. Ultra-high performance contains a high percentage of discontinuous internal fiber reinforcement. This reinforcement allows ultra-high performance concrete members to maintain tensile capacity beyond cracking of the cementitious matrix. Another innovation in ultra-high performance concrete is it has a much lower water to cement ratio than standard concrete. This helps aid in the mixing process on site. However, the reduced water content in UHPC mix requires careful curing practices, so included water does not escape prior to hydration. Another innovation of ultra-high performance concrete is it can be mixed in standard concrete mixtures. Although ultra-high performance concrete requires increased energy input compared to conventional concrete, mixing time will be increased. This concern is addressed through the use of high energy mixer or by lowering the temperatures of the constituents and partially or fully replacing the mixed water with ice. These procedures have allowed UHPC to be mixed in conventional pan and drum mixers, including ready-mix trucks. Once again, this allows UHPC to be mixed on site. Next, we examine case studies. The importance of case studies are they provide concrete results from testing and other research to support an idea or claim. The first case study that we will look at is the National Precast Concrete Association. It states that in the United States, the only large-scale implementation of ultra-high-performance concrete in bridge superstructures is by the U.S. Federal Highway Administration. However, in Europe and Asia, engineers have taken advantage of improved material characteristics found in UHPC. The question is, what is preventing U.S. engineers from taking advantage of UHPC designs? To understand, the NPCA case study evaluates material properties, current research, production techniques, and other factors that influence the use of UHPC. The first test the NPCA case study cites was done by the Michigan Technological University, and it's a test of 4 separate curing methods. The first is a 48-hour thermal steam treatment at 90 degrees Celsius and 100% relative humidity. The second, ambient air curing. The third, a delayed thermal steam treatment, which is a 10-day delay before curing. The fourth is a double delayed, which is a 24-day delay before curing. The results of these tests were thermally treated specimens attained an average compressive stress greater than 29,000 psi, independent of onset of curing. Air-cured specimens at 28 days had a compressive stress of 24,000 psi. All specimens showed negligible chloride ion penetration. All specimens were freeze-thaw resistant, and the compressive strength, Poisson's ratio, and modulus of elasticity did not vary after UHPC was thermally treated. These results mean that a precast manufacturer may be able to produce several UHPC elements during a short time period and then transport and cure them at a later time. This provides a greater flexibility in both the casting and curing of the material. The next citation in this case study was of the Federal Highway Administration's UHPC research program. The findings were that UHPC with steel organic fibers can produce bridge decks that are not susceptible to corrosion-induced deterioration. This means a longer service life and lower maintenance costs. The case study then moves back to the initial question and states that the implementation of UHPC in U.S. is progressing slowly for 3 reasons. First, the lack of U.S. design codes. Second, risk perception and lack of familiarity. And third, the high initial cost. Ultimately, this means U.S. engineers' hesitation is a result of responsibility for public safety versus lack of history of proven performance. The study also cites other evidence that supports the use of UHPC, such as green innovations, including reductions in CO2 emission, long-term service lives, and expected minimal maintenance and reduced life cycle costs. And we'll mention these in the examination of the benefit analysis. The main question when examining benefit analysis is the higher initial material cost of ultra-high performance concrete justified by the material's superior mechanical properties and other characteristics? The results from material testings and case studies have proved that greater compressive strengths and tensile strengths are allowable, which means smaller members and longer spans. Also, faster curing time results in earlier stripping of formwork. Internal fibers make UHPC more corrosion resistant. It has longer service lives, lower maintenance costs, and also mention the green alternatives.
This concludes our analysis of ultra-high performance concrete as an innovative technology.